Hello, my name is Atsushi KANEKO from Shinshu University, Japan. I will start my presentation entitled Conversion of Elastic Energy Stored in the Legs of a Hexapod Robot into Propulsive Force. This study proposes a novel leg design method to increase the speed of legged robots using flexible materials. The method can design flexible legs that convert the elastic energy stored under ground reaction force into propulsive force. The experimental results show that the legs designed by this method can increase the speed up to 89% compared with existing methods. Let me explain the background of this study. Inspired by animals, many legged robots with flexible and elastic legs have been designed to achieve high locomotion performance. Animals can use the elasticity of the leg for efficient locomotion. Many design methods for robotic legs have been developed and investigated to mimic animals' efficient mechanism. In these methods, the robot's body is simplified as a mass point and the leg as a spring. This simplified model is called the spring-loaded inverted pendulum (SLIP) model. The spring constant is designed as stiff as that of an animal's leg of the same mass. R-Hex is the pioneering and great example, featuring C-shaped flexible legs. Now I will talk about the purpose of the study. This study proposes to add a torsion spring in the SLP model to increase the propulsive force by designing the torsional and linear stiffnesses appropriately. In this paper, the newly added torsion spring is called leg torsion spring, and the spring inherited from the SLP model is called leg linear spring. The illustration describes how the torsional spring can produce propulsion force. In A, the leg touches the ground. The torsion spring is compressed, and elastic energy is stored in it. In BC, the elastic energy is released, which in turn pushes the body forward. Now I will explain how to achieve it, propose the method. We assume that by designing legs so as to kick the ground strongly backward and horizontally due to elastic force, the robot can achieve a large propulsive force. For this, the legs must store a large amount of elastic energy just before they kick the ground. For the elastic force to push the body forward, the legs must deform in such a way that the toes project forward, as shown in figure A to C. To realize such deformation, here we propose a D-shaped leg. We designed the D-shaped leg by combining a C-shaped leg, similar to the R-Hex leg, and an I-shaped beam. Now let me move on to the simulation model. The D-shaped leg is designed by a combination of physical simulation and optimization with the following two policies. Policy 1 is to maximize the elastic energy stored in the leg just before kicking the ground. Policy 2 is to adjust the stiffness of the leg linear spring based on the mass of the robot, as well as R-Hex design. For physical simulation, entire D-shaped leg is modeled as torsion and linear springs. This is a 2D simulation model of the D-shaped leg. In this study, we perform a static simulation that reproduces the deformation just before the leg kicks the ground. To perform the simulation and optimization, we use Rhinoceros 6, a 3D CAD system, and its plugins, which include a physical simulator and optimization functions. The optimization was performed using a multi-objective genetic algorithm named Octopus. Please look at this figure. This is the rhinoceros screen. We define the y-axis and x-axis as shown in the figure. The model was fixed at the top 2 points, and 0.7 newtons was applied to this point as the normal force from the ground. The plots in red show the D-shaped leg before deformation. The plots in green show the D-shaped leg after deformation. The stiffnesses of the torsion springs in each C-shaped and I-shaped part are used as variables in the optimization. The objective function 1 was set to maximize the elastic energy stored in the leg after deformation. E is the sum of the elastic energy stored in the leg. K theta is the stiffness of the torsion spring. Delta theta is the angular displacement of each torsion spring. KL is the stiffness of the linear spring, and delta L is the length change of each linear spring. The objective function 2 is to achieve desired leg linear spring stiffness proposed in our hex. In particular, we set to minimize the difference between the y displacement of the leg's toe and the desired displacement. The desired displacement was determined from the stiffness of the appropriate leg linear spring. Here is a video of rhinoceros and its plugin while running an optimization algorithm. First, the stiffness is changed by an optimization plugin. Then a physical simulation is performed. Finally, the deformed shape is displayed, and the optimization plugin evaluates it. This process is repeated. This right plot shows the progression of the multi-objective genetic algorithm actually used for the prototype. The C-shaped and I-shaped parts were fabricated so that they achieved the stiffnesses by the optimization. Here, I will show you the prototype with 6 D-shaped legs, whose stiffnesses are defined by the optimization. We also fabricated the C-shaped legs to compare the locomotion performances with the proposed method. The comparison was made by changing the legs. Each of the 6 DC motors fixed to the body rotates one leg to perform locomotion. The 6 legs are divided into 2 sets, red and blue, and each set is synchronized. The phase difference between the red motors and blue motors is 180 degrees, so the red and blue motors rotate anti-phase manner. There are 4 essential parameters for a tripod gait. The walking cycle is Tc seconds. There are 2 phases in the cycle, the fast phase and slow phase. In the fast phase, the motor rotates the leg by 2 pi minus phi s radians during Tc minus Ts seconds. In the slow phase, the motor rotates the leg by phi s radians during Ts seconds. When phi s is 0, the range from this angle to this angle corresponds to the slow phase. Otherwise, the angle of the slow phase is shifted by phi o. In this study, Tc was set as 0.76 seconds. Also, Ts was set as 0.38 seconds. Experiments were conducted for different values of the control parameters phi s and phi o. The controller parameters of previous studies are used as a reference for control of the prototype. Now I will show you the highlight data of the experiment. This video shows that the D-shaped leg increased the locomotion speed. In this experiment, the prototype moved for 5 periods, which then the distance traveled was measured. The speed was obtained by dividing the distance traveled by the elapsed time. We repeated the experiment 3 times with each parameter setting and obtained the average value. Now I will show you the experimental results. We tabulated the experimental results with various parameters. Table B shows the locomotion speed of the prototype with the D-shaped legs, the proposed method. Table C shows the locomotion speed when utilizing C-shaped legs, the related method. The horizontal axis is phi s, and the vertical axis is phi o. The units are meters per second. Table A shows the ratio of the proposed legged speed to the C-shaped legged speed. The units are percentages. Greater than 100% indicates that the proposed legged speed is higher than the C-shaped legged speed. The results show that the D-shaped legs increase the locomotion speed by up to 89%. In the previous video, I showed you the experiment with this parameter setting. These are snapshots of the prototype during locomotion. The red colored legs are the states just before kicking the ground. These figures show that the D-shaped legs deform as intended in the design phase. Due to the elastic force produced by this deformation, the D-shaped legs seem to have increased the prototype's velocity. Finally, I will conclude this presentation. We propose the method of designing legs to improve propulsive force through the use of D-shaped legs. In this design method, the stiffnesses of the legs are determined by simulation optimization. In the future, we want to add distribution of the stiffness when performing the simulation and optimizations. We will also change Tc and Ts and compare the moving speed. This study was supported by following grants. Thank you for listening.